All right, welcome to the brain and the nervous system, especially the brain part two. I hope you completed the part one lecture and got a few basic insights about the nature of the brain. I certainly hope you've also done the reading because this part of the lecture overlaps a great deal with the second set, I think it is, of the readings. We're going to talk now a bit about the aspect of the nervous system known as neurotransmitters. Exactly by what chemical process do different neurons in the brain, or do, let's say, motor neurons in the brain communicate with your hands, communicate with your eyelid, with your eyelid, so that you can blink. So how exactly does nerve transmission happen in the brain, and how do signals get from the brain to the various parts of the body that your brain has to move around? So again, having a little bit of a snag here. Let's try that again. There we go. We're going to talk about the fact that nerve transmission, communication between neurons, requires neurotransmitters. These, of course, are chemicals that bridge the synaptic gap and make it across that synapse very quickly. And they convert an action potential in a sending cell from an axon to electrical activity that's picked up in the receiving cell. And that receiving cell can make a decision, fire or not fire. Okay? As I hope you recall from reading your textbook, there are about 70 different neurotransmitters. Every couple of years, somebody discovers a new one. I'm not sure when the list will be done. It's kind of like the moons around Jupiter used to be. I think we've discovered them all now, and I think Jupiter might have about 70 moons, maybe even more. But there are a bunch of them, and I know that can be overwhelming. So we're just going to talk about my five favorites, or five of the six or seven that I know pretty well. And we're going to begin with one that you're already familiar with. We're talking about, communication here. We're going to begin with acetylcholine. And I'll just draw your attention to the fact that I put a little note here that says read all about it, because in some lectures I have to skip over the neurotransmitters and make people read. In your case, because we're doing this quickly, because this is pretty technical, I feel like I should take a little time and cover at least the five that I cover in the book. The one that I mentioned first in your textbook, that my co-author and I mentioned first, is acetylcholine. It's one of the first ones discovered. Cajal knew all about it. It's involved in things like the initiation of motor movement. Now, dopamine does that too, but it's one of the big ones for the initiation of motor movement. It's also involved in attention, learning, and in sleep. And I've shown you a few images here I'm going to that illustrate, as a reminder, that acetylcholine, not some cousin of it, acetylcholine itself is the neurotransmitter that allows the Venus flytrap to catch its prey. Acetylcholine is also the neurotransmitter that allows a sprinter to pay careful attention to the starting gun and get a good start to win that gold medal, or in my case, would be an eighth place medal in the regional track meet, not in the Olympics. But it's involved in attention. It's involved right now, I hope, in paying attention to this lecture. I hope it's involved in learning, because I hope you are learning. And when you get exhausted and you can't learn anymore, it plays a big role in things like sleep. So there's our image for learning. There's our image for sleep. And I feel compelled to mention just one more thing about acetylcholine. Some people call it the handyman. We should probably say handy person to be gender neutral. The neuron that does a bunch of different stuff. And just to give you another example, acetylcholine is the main neurotransmitter of the parasympathetic nervous system that lets you do things like rest and digest instead of things like fight or flight. And so acetylcholine does a bunch of stuff. Without it, you definitely couldn't survive. All right, I'm going to take a short pause here, and then I'll be right back with you. All right, sorry for that brief interruption, but I had a kid who needed to get to bed, so I had to offer at least a good night. So we're going to, speaking of bed, she's going to go to sleep right now. And so I hope she can sleep well, and I hope she gets some help from acetylcholine. And by the way, for those of you who speak a little Spanish, this is a nice little way to summarize dice cálmate al cuerpo, that it's the neuron that tells your body, calm down, it's okay, everything's fine, get some rest. Okay, so that's one of the many things that acetylcholine does for you. All right, let's keep moving. I hope. My PowerPoint's not been my friend today, but we're going to keep moving. Oh, that's just an arrow to show you that part of rest and digest is, of course, sleeping. All right. The second neurotransmitter I'd like to talk about just a little bit is dopamine. And dopamine, it also regulates motor behavior. So when people suffer from Parkinson's disease, for example, you can sometimes give them drugs that activate, that are agonists, that kick up the activity of dopamine, and it can give people tremendous relief sometimes. So dopaminergic systems operate on dopamine. They run, in a sense, on dopamine. And one of those systems is motor behavior. Motivation, pleasure, and a lot of basic emotions also involve dopamine, especially positive emotions like happiness, excitement. That includes sexual pleasure. Lots of positive emotions happen because of the activity of dopamine. And so, for example, if you think this person here is beautiful or hot, or if you think he is beautiful or hot, they empirically they are, by the way. I've gotten ratings for them. They're beautiful people. Probably not quite as beautiful as they look in the photo because we Photoshop those things. But if you find them attractive and it makes you happy to look at them and make you happy to speak with them, then dopamine is involved in that. If you'd much rather just have an ice cream cone than hang out with a hot person, dopamine can help with that too. It's the pleasure neurotransmitter. It's not just, the pleasure of meeting somebody or being attracted to a person. It's also the pleasure that we get from eating something delicious or getting a giant pile of cash. So dopamine is involved in a lot of different systems. If you stand on one foot and keep your balance, if you taste a delicious apple pie, then your neurons are communicating with one another by using dopamine. Now, other neurotransmitters will also be involved, but the way I remember dopamine pretty well, and I think I also put this in your textbook, is if someone says, dude, that car is really dope, he doesn't know it probably, but he's saying, that car is so cool that it activated the dopaminergic pleasure regions, the reward centers of my brain. It's fun just to look at that car. Good, cool car, dude. So that's dopamine. And again, even though I already said this, if you meet a person that you find very attractive and you'd like to get this person's number, you wouldn't be doing that if you didn't have dopamine. Dopamine's involved in that as well. Okay, so number 2, dopamine. Okay, what about number 3? Number 3 is oxytocin. Now, oxytocin is also a hormone. In fact, if you've ever been with a person who's giving birth, as I have a couple of times, and you've heard the healthcare professionals say it's time to give her Pitocin, Pitocin is oxytocin. So you artificially give people oxytocin to speed up birth. I don't want to wax too political about this, but that's actually most of the time a very bad idea. It dramatically speeds up the labor process, and women go into physical distress. Their babies go into distress. If you just waited for nature to take its course and you didn't routinely give people Pitocin, births would be safer for mothers and babies. I'm going to write a whole book about that someday. I do work in that area. But for right now, the important point is oxytocin is a hormone. It's also a neurotransmitter, and it's crucially involved in everything from birth and breastfeeding to human bonding. And if you want to hear a really fast talker talk about this, now when I was young, I spoke this quickly. I have to slow down as I get older, but let's listen to a very fast talker tell us a little bit about oxytocin, I hope.
It's high time we here at SciShow dispel this myth that YouTube is all about cat videos. Fact is, we like dogs as well. We've talked about the science of canines, like their health and their behavior and how they evolved alongside humans to become our companions and helpmates and friends. But this week, scientists said they may have pinpointed why humans tend to have deep emotional bonds with dogs more than any other kind of animal. It turns out that the hormonal response we have to our dogs is the same chemical connection we have with our own babies. So yeah, those people who dress their dogs up in cozy sweaters and and talk to them in complete sentences and basically treat them like their offspring? That may not just be a matter of being like a dog person, it may also be a result of oxytocin. Oxytocin is a hormone released by the pituitary gland, and it's probably the most important chemical in your body when it comes to relationships. The secretion of oxytocin has been associated with the feelings of comfort and security. It also fuels intimate behaviors, especially sex, but its strongest influence probably has to do with parenting. Oxytocin stimulates contractions during childbirth, produces breast milk during nursing, and both women and men are bubbling over with it when they care for their newborns. So oxytocin does a lot of different things, and according to a team of Japanese researchers, people also get amped up on oxytocin when they're with their dogs. But instead of being triggered by things like feeding or nurturing, the team found that people and dogs both release oxytocin when they make eye contact with each other. In one experiment, the researchers put dogs in a room with their owners and watched them interact for half an hour. Then they measured the oxytocin levels in the urine of both the dogs and the people, and they found that regardless of how much the people interacted with dogs in other ways, like talking to them or petting them, the dog-human pairs that had the most eye contact also had the highest levels of oxytocin. In the second experiment, the scientists gave the dogs a dose of oxytocin and then put them in a room with their human friends along with some strangers. The female dogs that had been treated spent much more time maintaining visual contact with their people. And after a half an hour of being stared at with adorable puppy eyes, the owners of the treated dogs had higher levels of the hormone too. Now the researchers point out that none of this happens with wild canines. Even wolves raised in captivity don't show this intimate hormonal response to the people who raised them. So this research suggests that humans and dogs have found a way to create a feel-good feedback loop, reinforcing our mutual bonds by driving each other's levels of love hormone. A little bit weird? Sure. Hashtag cute? Definitely. There was also some unusual news this week about what's probably humanity's second best friend, our gut.
All right, we're going to skip the discussion of gut bacteria. In fact, I never get that far, so I'd forgotten it was even there. But notice he gave us some information about oxytocin, and he emphasized the aspect of oxytocin's function that has to do with human bonding. And so you learned that we have deep emotional connections to dogs, very much like the ones we have with people, but we don't have those with wolves. And it's because wolves don't have those with us. Wolves don't care about us. Wolves have not lived with us for 8,000 years, and we haven't selected the ones that are really nice to us and care deeply about what we do. So you can rear a wolf as a pet and it probably won't eat you, but it's very unlikely to ever love you the way a Chihuahua or a Boxer or a Lab will love you. So that's oxytocin. All right, that's number 3. It always takes a second to get going here. There we go. Number 4 is serotonin. Serotonin affects mood and arousal. It affects eating, aggression, and sleep. So you do see serotonin doing some of the things that some of the other neurotransmitters do. So mood and arousal are connected to dopamine. Serotonin is connected in a somewhat different way to mood and arousal. So serotonin is also connected to sleep. Acetylcholine is connected to sleep. We're seeing here that it's not like each neurotransmitter just has one job. It has many jobs, and that's both good and bad. It's good because our brains are flexible and we can do lots of different things and they're complicated. It's problematic in the sense that anytime you give a person a drug for, let's say, a clinical disorder, and selective serotonin reuptake inhibitors, which you read about, are one drug that we give people when they have clinical depression, that can help a lot of people break out of clinical depression, but it can also have lots of side effects. So, for example, one big side effect of serotonin, of selective serotonin reuptake inhibitors, like Prozac for a lot of people, is it greatly reduces people's sex drive. If you're an 88-year-old widow or widower and you don't really want to have much sex anymore, that's not a big deal. You don't even have a partner. But if you're a 25-year-old newlywed, that's probably a very big deal. So any chemical that intervenes, any drug that has a psychoactive effect, is doing it through its interaction with neurotransmitters. And unfortunately, most drugs that affect a particular chemical pathway or chemical system, like serotonin, like acetylcholine, they're also going to have effects in parts of the brain that were unintended by the people who discovered the drug. So side effects happen precisely because most neurotransmitters have multiple jobs. All right, so that's serotonin. I think I had a little bit more to say. Yeah, I've just got some examples here. So you see Shaq here yawning. I guess he's sleepy. You see that giant sandwich that's making me hungry. You know, I just had dinner a couple hours ago. You see a couple people boxing or fighting, and of course you see this little toddler sleeping. I don't really, I don't, I can't resist showing you a little bit of this boxing match because it's a classic match in the history of boxing. But it's really just to show you a little bit of aggressive posturing.
Very simple instructions. And finally, it's Hagler against Hearns.
The camera's going to have to go.
Eloquent simplicity by Richard Field. Let's go.
He knows, they know.
Okay, so look at the look that we're seeing there. Now, by the way, when I was much younger, I was sort of a fan of boxing. This fight is like a 30, 40-year-old fight. It happened probably in 1983 or something, so it happened a long time ago. I watched that fight happen. I don't even remember who won. Okay, so it's not important who won or who didn't win. It's just an example of the fact that serotonin does play a role in aggression. And there's debate, for example, about the degree to which certain treatments for depression can make people violent either toward other people or toward themselves. I lean toward trusting the experts who say that either doesn't happen or doesn't happen very much. And some of the ways in which it can happen can be artifactual. So, for example, sometimes people taking SSRIs for depression do commit suicide. That does happen because being depressed puts you at risk for suicide. But many experts think the reason it happens is when a person is profoundly depressed, they can't even get out of bed in the morning. They can't make a plan to commit a suicide. But once they start coming out of their depression, because the drug is helping them, if their caregivers and psychotherapists don't keep a careful eye out, they might get up just enough energy and just enough clarity of thought to put together a plan to sadly take their own life. So my interpretation, or at least the experts I trust the most on this topic, say serotonin in the form of drugs that help people help treat clinical depression probably don't have the side effect of making people violent. That's the consensus view among most experts. Okay, I think that was number 4. That leaves us with 1 to go. And the 1 to go is going to be endorphins, if I can get to it. There they are, endorphins. Endorphins are chemicals that you could think of them as endogenous morphine if you wanted to. They're chemicals that affect our emotions and especially pain perception. They reduce pain. They make us feel satisfied, happy, or even euphoric when otherwise we might feel horrible. So if a person has a natural birth, or if a person bikes 100 miles in a day, if a person runs a half marathon, that person is definitely going to benefit from endorphins because they're natural painkillers that help people fight through a very difficult process and sometimes feel very good at the end of it instead of feeling physically horrific and miserable in tremendous pain. So if you look here at these 2 images I'm going to share with you, if you follow long distance running as I do sometimes, because I used to be a casual long distance runner and I ran a little bit of track in college pretty slowly. I love distance running. I don't love doing it. I've run a marathon or 2, but I didn't enjoy it. But if I could run as fast as Eliud Kipchoge, or if I could run as fast as Jemima Sumgong, I would probably have done a lot more running in my life. I did enough running to blow out my knee, by the way. I had knee surgery almost exactly 6 months ago and got an artificial knee because I used to run a lot, albeit slowly. And I can tell you that if you get into the 15th mile of a 20-mile run, endorphins do thankfully often kick in. I should also mention just briefly here, I just learned a couple of weeks ago, I guess I missed this, I think it was back, I want to say in maybe November, Eliud Kipchoge, with the help of a team of like 8 other runners, breaking the wind for him and people coming up on bicycles and handing him his gels and his water and his Gatorade, he ran a marathon. He's the 2016 Olympic champion. He ran a marathon in just under 2 hours. Now, that was with a little bit of help from other people, but he can run the marathon at a mile pace that would win many high school track meets. Okay, it might even take him to state. He probably wouldn't win the state championship in high school with that 440-ish mile he runs in his amazingly fast marathons. but it's an amazing pace. He couldn't do that. Jemima couldn't do that without the help of endorphins, nature's painkillers. All right, there we go. Okay, so I keep saying read all about it, but I decided not to make you, I mean, you did read about it. I hope you read about it, but I hope this reinforces it a little bit. And I don't know if I said this in the reading, even though I reread it this morning, but I'll give you a little mnemonic device here. Mnemonics are little rules or tricks for remembering things. So if you want to remember these 5 neurotransmitters, think of a dose of a drug that might have a psychoactive effect. There's A, D, O, S, and E. And unless I'm forgetting, that's the order in which, of course, I just gave them to you. So if that helps you remember the big 5, those are the only 5 neurotransmitters that I believe I covered in the textbook. I don't think I covered any others. At least I didn't put them in bold. And they're the 5 that I expect you to know for the first exam, just to give you a sense of the variety of chemicals in the brain that allow neurotransmission or nerve transmission to happen. All right, that's that. We're going to shift gears a little bit here and talk about the fact that parts of your brain are not just parts. So of course, that's compartmentalization. We're going to talk in a good bit of detail here. I'm going to about the compartmentalization of your brain, the fact that different regions of the brain have very different, highly specific functions. So we're going to talk about that a bit. And I should mention, I remember reading this again this morning. It is the case, of course, that people can often recover from pretty serious brain injuries. But if the brain injury is big enough and you're old enough, if you've already reached full adulthood and your brain's not developing anymore, it's either difficult or it's completely impossible to recover from certain brain injuries. And I'll give you a couple examples of that. I briefly mentioned in your textbook the story of Phineas Gage. Phineas Gage lived, I think, in the he got his accident in the 1850s or thereabouts, not long before psychology became a field. He was a very productive, very bright, very hardworking manager. I guess you could call him a foreman of railroad workers. And he was a hard worker himself. He didn't just give the jobs to the people building railroads, like blowing away huge chunks of a mountain. He would get in with them sometime and do the work himself. And on one particular day, he was working in some stone, probably something like limestone, and he or his assistants had drilled out a giant hole. He had packed it full of gunpowder. And now the next thing you're supposed to do, you put in the gunpowder and a fuse, a big fuse. Then you put in a bunch of sand on top of the gunpowder, and you take a giant iron rod, a little bit bigger than a broomstick, and you tamp the sand down on top of the gunpowder to pack it in like a firecracker or like a stick of dynamite. And when you do that, and you do it properly, and you run your fuse very far away from there, because these explosions are massive, they're powerful, and you press the plunger just like in the old cartoons, it blows up the rock and you blast through the mountain. And that's one of the things you do to build a railroad. On this particular day, something must have distracted Phineas Gage. He put in the gunpowder, he put in the fuse, and without putting the sand in, he grabbed the iron rod and he pressed it down very firmly. And of course, it created a spark. So that iron rod became a giant bullet or cannonball. It blasted through, I'm pretty sure it was his left eye, blasted through the top of his skull and landed like an eighth of a mile away. And of course, you would think he would die for a couple of different reasons, but he didn't. He also survived the infections that many people get. This is back in the day before we had good ways of treating infections and before we knew what caused infections. So somehow Phineas Gage survived. He wore a patch over his left eye for the rest of his life. And so, of course, he lost that eyeball, and he lost a giant chunk of what is now known as the prefrontal cortex. And what we learned from him, and I mentioned this in the book, so I'll be brief for this part because I'm being redundant, it completely short-circuited his ability to regulate his emotions. He had been a very thoughtful, cautious, responsible guy. And if you'll give me permission to say this word, because I grew up in rural Georgia, He became a redneck. He wanted to party all the time. He drank too much. He spent his money. He gambled. He cursed like a sailor. He went from being a very thoughtful, responsible, hardworking dude, getting his paycheck and going out immediately and blowing it and not thinking about tomorrow. So when he got damage to this area of the brain, the prefrontal cortex, he completely lost his ability to engage in risk management. Okay, so he did whatever sounded fun or interesting right now, and that led to lots and lots of problems for him, and he never got over it. Okay, even if it happens today, there aren't any drugs you can give that will repair that because the amount of brain damage was just too severe. Now, he could still do math. He could still think logically. If you gave him an IQ test, he would still score, I'm sure, above average because he was a bright guy, but he could no longer regulate even the most basic emotions, and it made his life very difficult for the rest of his life. So that's an example of the specificity of one particular brain region, this area right here behind your forehead, that helps you regulate your emotions. I should also mention that unless you're about 25 years old or older, your prefrontal cortex is not fully developed. So you're a bigger risk taker right now at 18, 19, 17, 20, 21 than you will be when you're 28 or 30, when your prefrontal cortex has completely matured. So the next time your friend dares you to do something that feels risky and you catch yourself about to do it, say, let me wait for my prefrontal cortex to mature a little bit more and ask myself if I should do that in 4 or 5 years. And the answer might be maybe you shouldn't. Okay, so that's the prefrontal. Just put on my dad hat, didn't I? Sorry about that. So at any rate, that's the prefrontal cortex. I can also tell you a little bit about damage to Wernicke's area. That's an area of the brain that's involved in speech, but in this particular case, if you get damage to Wernicke's area in particular, it's about right here, a little bit behind the left ear of most people. You continue to speak. In fact, you speak smoothly and fluidly, but your speech becomes gobbledygook because you no longer can understand the meaning of words. You don't get grammar, you don't get syntax, and I think I forgot to double check this for you. I'm gonna see if I can show you this video. I may be able to, I may not. Let's see if I can show you this video. I want to say this guy's name is Byron. Let's see if we can see a guy with Wernicke's aphasia, a guy who had a stroke that damaged his brain. I'm not going to make it big because I may not be able to get out of that.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talk with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So we're on a cruise and we're about to
We
get to
will
Juneau.
store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing. Like here?
I'd like my change for me and change hands for me. It would happen. I would talk with Donna sometimes. We're out with them.
So you can see here, now this is tricky. Let me get back to the lecture if I can. You can see here that Byron has tremendous difficulty understanding the most basic sentences because let me in here. All right, I don't know if I may have to try Control C. I knew that was risky. I took a little risk. I'm going to pause this recording and get it back, and I'll come right back to you. All right, I guess one advantage of having a course online is when I pause it, you don't have to wait for me to fix the problem. So I was able to fix the problem and get back here. So my apologies for that. But you can see in the case here of Byron, he just doesn't understand even the most basic questions anymore. He can speak fluidly. He's comfortable. Now, if you saw Byron speaking and you didn't know more about him, you might think that he had schizophrenia. His speech is disordered and quirky and unusual and illogical. He doesn't have schizophrenia. He had a stroke that damaged Wernicke's area, and it didn't keep him from producing speech, but what he produces doesn't make sense to us because he himself can no longer understand the meaning of what other people are saying or the meaning of what he's producing. And no matter what kind of therapy he gets, he's very unlikely to have a big improvement. Now, if he were 11 are 8 or 3 and had a stroke or brain damage to that area, it's very likely his developing brain could compensate and neighboring regions might start to do that work. But if he had the stroke at age, let's say age 60, and if the stroke is big enough, he's never going to recover from it because that particular area of the brain has that very particular job. And if you get damage there, you're going to lose that ability. So that's another example, of course, of compartmentalization. And I forget if I had a third example for you. Let's see. Let's see if we did. Oh yeah, the third example I'd like to share with you just briefly is the fact that if you get damage to the substantia nigra deep in the center of your brain, you can get a lot of damage to the substantia nigra. You can lose half of the cells in your substantia nigra, nothing happens. You can lose 80% of those cells, and for most people, nothing happens. But there's a break point of about 90% cell death. Once you have only 10% of those cells living and healthy, you're going to start to show symptoms of Parkinson's disease. You're going to get diagnosed with that disease. And so, like Michael J. Fox and a couple of other famous people, you're going to have tremendous difficulty doing things like initiating movement. And without the benefit of chemical interventions, some drugs that facilitate dopamine can help with that. And there are actually surgical treatments now where you can insert electrodes into people's brains that in some cases for some patients have given them tremendous relief from Parkinson's, but ultimately it's a degenerative disease that leads to people's death. Okay, so it's not a very happy story if a person gets Parkinson's. I guess if there's any good news there is that it rarely happens to very young people. So it's typically a disease of people who are senior citizens. So a bit like Alzheimer's that way. Now it can happen to people younger. Michael J. Fox was pretty young when he got it, but if you get Parkinson's disease, there are a few things that modern medical technology can do for you, but sooner or later, for most people, it's going to be fatal. All right, so that's compartmentalization. Oh, the fourth point I want to make about compartmentalization, and we will delve into this quite deeply, is the fact that, as you already know, I hope, your brain is divided into two halves that look a lot alike, but are responsible for somewhat different jobs. That, of course, is called lateralization, and we're going to delve into that here in some detail. All right, your brain is compartmentalized, and one of the ways in which that's true is through the fact that you have two hemispheres that are lateralized. Okay, here they are. Your brain, as I said, is neatly divided into two halves, a right and a left, and those two halves have somewhat different functions. Now, sometimes people in the media greatly exaggerate just how different they are, and there are people whose brains are barely lateralized at all, and there are people whose right and left halves of the brain become equally activated when they speak or do a math problem. But for most of us, especially most right-handed people, it's the left hemisphere of the brain that's responsible for producing and understanding language, for doing mathematics, for engaging in logical reasoning. And it's the right hemisphere in most right-handed people, and most left-handed people too, but not quite as many of them, that the right hemisphere is responsible for face recognition, music, spatial reasoning. Those are very different functions. Now, those two hemispheres communicate with each other a lot through something called the corpus callosum. It's a bundle of millions of nerve fibers that go through the center of the brain and let the hemispheres communicate, but they do have somewhat different functions. And I hope I can help you appreciate that a little bit by asking you to think about four very famous women. I'm sure you've heard of Beyonce. You know more about her than I do. You probably heard of Maya Angelou. You probably heard in 4th or 5th grade or 10th grade science class about Marie Curie. She got 2 Nobel Prizes, by the way, in science. She's the only scientist to win 2 different Nobel Prizes in science. I think she got one in chemistry and one in physics, by the way. So I hope you've at least heard of her. And you may have heard of the painter Georgia O'Keeffe, who lived until something like 1995, made these really cool, interesting paintings of desert scenes. So we have a singer, a scientist, an author, and a painter And I'd like you to think about what they do for a living or did for a living and ask yourself, what would be a disaster for Marie Curie or Beyonce or Maya or Georgia? Where's the last place they would hope to get a bad stroke? Okay, so I hope you can agree. Now, Beyonce is an interesting case here, but I hope you can agree that Beyonce is best known for producing music, and that means it would be a disaster for Beyonce to have a stroke on the right side of the brain, especially if it was the part of the brain that's heavily involved in understanding and producing music. Now, Beyonce also, I'm pretty sure, writes some of her own songs, so she doesn't want to have a stroke that makes her lose language either. But if she's a great dancer and she's a great singer, she does not want to get damage to the right hemisphere of the brain. Marie Curie, I don't think it'll take you too long to figure this out. She definitely would not want to have a stroke on the left hemisphere, in the left hemisphere, because she might lose her ability to do mathematical calculations. She might not be able to speak anymore. She might not be able to write or read anymore. Those would be devastating to a scientist. If you can't engage in logical reasoning, you're not going to win a Nobel Prize in science. So that's Marie Curie. Author Maya Angelou probably didn't do a lot of math in her career because she was a writer and a poet. And so for Maya Angelou, it would be a problem if she had anything that messed up her that messed up her language ability. So that'd be a problem. And that leaves, of course, Georgia O'Keeffe, who I assume was really good at spatial reasoning and representing things. You can't be a painter without having a good sense of how things look and how things fit together into a gestalt whole. So for Georgia O'Keeffe, it would have probably been terrible if she had a stroke that happened on the right half of her brain. So again, it's not a simple black and white difference, but yes, it is the case that the right and left halves of people's brains have somewhat different jobs, even though they also communicate with each other quite a bit. Okay, so that's that. I'm just showing you where Wernicke's area is, and that Broca's area is quite a bit forward, but of course in the same half of the brain. All right, I think that's that. Again, big picture, that tells us that brains are neatly compartmentalized in very important ways. All right. A kind of fun way, I didn't practice this earlier today. I probably should have. A sort of fun way to see that your brain is lateralized has to do with what's called lateral interference effects. And so I'm going to march through something with you here. I'm going to ask you to stand up. I guess I better stand up if I'm going to ask you to. I don't know if this is going to work, if I can reach, but I'll try it. I'm going to ask you to stand up. And then I'm going to ask you to make a clockwise motion with your right hand. Now, you can do it with me or you can wait and do it later, but I'm going to do it to give you an idea what we're talking about. All right. Then I want you to stand on your left foot. Now, that's a bit tough for me because the left leg is the one where I got a new mechanical knee just 6 months ago, almost to the day, but I think I can do it. I am doing it, I promise you. I'm moving my right hand. So far, so good. Now, if I want to, I'll stabilize myself a little. All right. Then I'm going to make the same circular motion that I'm making with my right hand with my right foot. Now, you can't see it, but I'm doing it, I promise. I'm moving my right hand in a clockwise circle. I'm moving my right foot in a clock. In fact, as I do it, I'm bumping my chair, so let me move it. So I'm moving my right hand clockwise and my right foot clockwise. That's super easy. As long as I keep my balance, I can do it. Okay, no problem. But if I try to reverse the direction with my right foot, and I keep going clockwise with my right hand, I'm getting massive lateral interference effects. It's very difficult to keep moving my right hand in a clockwise fashion and to move my right foot in a counterclockwise fashion. That's really difficult. But here's what's interesting. If I stand on my right foot, okay, I just moved my right foot. In fact, let me get my chair in case I need it, in case I fall over. That's easier. Okay, I stand on my right foot, and I move my right hand clockwise. I can very easily, and I bet you can too, so please do try this at home. It's not very dangerous. Try to move your right hand in a clockwise fashion and your left foot in a counterclockwise fashion. And I just did that with no difficulty whatsoever, even at my advanced age. And so that's interesting. If I move my right hand in a clockwise fashion, it's very hard to move my right foot in a counterclockwise fashion, but I can easily do that with my left foot. The simple message behind that, and of course I stole this from my buddy Dave Myers, who's a very talented psychology author. In fact, I hated that my book is competing with his because he's amazing, but he gave me permission to steal this example from him. Getting back to the point, I can move my left foot counterclockwise very easily when I'm moving my right hand clockwise, because the initiation of movement for those activities are happening in opposite halves of the brain. The area of my brain that controls my right hand is a very close neighbor of the area of my brain that controls my right foot. But the area of my brain that controls my left foot is way over here someplace, very far away from the area over there. So you don't get any interference from brain regions that are far apart. You do sometimes get interference from brain regions that are neighboring each other. And so that's, I hope for you, a fun example of the fact that your brain is highly lateralized, that different parts of the brain are compartmentalized, I should have said, to do very different jobs. All right, and that's just repeating that if you switch feet, it should be much easier to do those two sort of opposite things. All right, compartmentalization, right? I hope you recall the sculpture that I showed you in your textbook of the either the sensory or the somatosensory homunculus. I forget which it was because there are different kinds of homunculi. The plural of homunculus is homunculi, by the way, I'm pretty sure. But the homunculus, of course, is a clever way to represent how much of your brain is devoted to perceiving, taking in, or controlling, moving different parts of your body. And I'll show you a different homunculus here, different than the one I showed you. The one I'll show you here is taken from a museum in Britain. But your homunculus tells you why it hurts way worse to get a cut on your lip than to get an equally big cut on your shoulder or your back, because it's because of the way that your brain is wired. So let's take a look at that. Now the one I have here is borrowed from a different book, so it's a little different. I put the fig leaf up here to keep that PG-13. Okay, so that was I sort of did it for fun, but just in case someone's offended by that. You can see here in this sculpture that his lips are gigantic, his tongue is gigantic, his eyes are big, and his hands are absolutely massive. And that's a way of representing in a sculpture the fact that the wiring of our brain is super detailed and intricate for the parts of the brain that control the human hand or that feel what happens in the human hand, but they're much, much less rich, and it takes up much less brain volume for, let's say, the part of your skin that's above your knee or your calf or your shoulder or your back. Okay, so you can see in this somatosensory homunculus that our brains are wired to make certain parts of the body very, very sensitive, but to light, to sound, to pain, to touch, whatever, but also to give us tremendous control. So we have amazing control of our hands and fingers, and that's true in part because our brains are wired in a very particular way that reflects that sensitivity. All right, so that's that. I think I already said that, but that tells you why you'd much rather get a cut on your back than on your finger. I don't want a cut anywhere, but I'd rather get a cut on my back than on my finger. And if you want to test yourself and have a little fun with this, you can do this. You need a person that you're living with, that you're in the same bubble as that person. If you put a blindfold on a person and have them gently poke your palm, for example, with either two fingers, if you can see it, or one finger, okay, most people can pretty easily tell on the palm that, oh, with their eyes closed, that's two fingers, that's one finger, I think that's three fingers. But if you do the very same thing on the person's back or their shoulder, even if they have on a tank top and it's skin to skin, it'll be much more difficult for them to tell, is it one finger, two finger, three fingers. Is it the eraser of one pencil or one pen, or is it 2 or 3? So you have tremendous sensitivity to tell what's touching one finger, but you're not nearly that sensitive if it comes to telling what's touching your back or the back of your leg, for example. So that's another example of the fact that the way your brain is wired has a big effect on your, in this case, your sensory experience or your amount of control over something. So I think we're getting close to the end here, by the way. We're there. That's it. So thank you for listening. This is a longer lecture, but I hope the fact that I had you do a couple things broke it up at least a little bit. And I will see you when we have our next lecture, which I think will cover, I've already forgotten, but whatever it covers, I know a lot about it. Okay, so I'll see you pretty soon, and we'll talk about, won't be evolution. I'm not sure. Okay, I'm completely spacing. It's getting to be late at night. I'll see you soon. Thanks. Bye-bye. Oh, wait, I just remembered. There is no other lecture. This is the last lecture until the exam. Now, you do have a reading on evolutionary psychology, and there's a quiz on that. But I guess I'm happy to say that we finished all of our lectures for Section 1, Module 1 of this remotely taught class. Congratulations. See you later.